Good morning, everybody. This is Roger Perchette. I'm the managing principal with Interface Engineering, and I want to welcome everybody to the next session of the Interface Engineering free high performance building webinar series. And just a couple notes, Interface Engineering, we're a 51-year-old engineering firm, multidisciplinary design. Our offices are in DC, Chicago, LA, Portland, San Francisco, and Honolulu, and we have a strong focus on high performance building design. So the webinar series has been extending now for a couple months. This is the 5th session in the series, so we're nearing our halfway point. And the course that you will be hearing today is an AIA accredited lecture. Interface is an AIA accredited course provider, and the course will offer one learning unit. You should have, when you registered, included your AIA number if you have one, and based on that AIA number, you will receive one learning unit that we will do the reporting for you, so you don't need to self-report. If for some reason you've neglected to provide your AIA number, you may email Emily Williams, that's Emily W at interfaceeng.com, and she will make sure that you get a certificate and that you are also reported to the AIA. So it is my great pleasure today to introduce our two speakers. The first being Mr. Craig Burton. Craig is a brilliant engineer. He's an associate principal with Interface Engineering. He's one of the leaders in our Chicago office as a licensed professional engineer and a LEED accredited professional. He also serves on the board of IBSA in Chicago. That's the International Building Performance and Simulation Association. He has his a bachelor's degree from Dalhousie University in Nova Scotia. And in 2014, Craig was named the top 20 under 40 for Engineering News Record magazine. He has 16 years of experience. I first met Craig, I think about 16, 17 years ago in London, and I may have been the person that convinced Craig to move from Europe to the United States. But through the years, I've had the great fortune of working with Craig on a number of exciting projects in the United Arab Emirates and China and Malaysia and here in the United States. So happy that Craig is with us today. I also am pleased to introduce you to Kulai Salitra. Kulai is also a brilliant engineer, electrical. He's an associate principal in our Washington, D.C. office. He's a licensed professional engineer in 6 states. He has his bachelor's degree from Polytechnica University of Bucharest. He's a certified electrical plan examiner, a certified commercial energy inspector, and he's also a Fairfax County, Virginia plan reviewer. In the DC office, we simply refer to Kulai as the professor. So some of Kulai's projects include the Net Zero Energy AGU headquarters, the Net Zero George Mason High School, the Net Zero Arlington County Group Home, and the Net Zero Sully Woodlands Education Center. So with that, I would like to turn it over to Craig Burton to take it away. And again, thank you both for sharing your knowledge with us today.
Well, thank you so much, Roger. I couldn't have given a more glowing welcome if I did it myself. Thank you, everyone that's joined us for the call, and hope that we are able to impart some useful knowledge today around our experience. This is the AIA course description to sort of clarify the intent of the lecture. I won't go over that, but I will go over the learning objectives so that everyone's clear as to what we're trying to communicate and the way that we'll do it. So the primary objective is to educate the audience on the fundamental components of a microgrid. You know, what are the pieces that we need to have a microgrid and the different forms it might take. We're going to cover the differences between alternating current and direct current as it pertains to the power that is distributed and stored and generated in a microgrid. We're then going to look at within direct current power systems, the different class of power that is utilized, class 1 or class 2 power, and how they can potentially bring benefits to a microgrid typology. We're then going to dive into a few examples of projects where we've actually built direct current microgrids and where we've looked at microgrids as a way of addressing various project goals. So the agenda that will help us take us through those objectives. First, we're going to cover, what is a microgrid. We're then going to go into the theory around alternating current and direct current. We're going to cover the real drivers behind direct current, the advantages. We're going to go through some efficiency gains calculations, address how controls can also be integrated into direct current systems in a way that currently is not possible with alternating current. We're going to show you some examples. We're going to talk about an emerging direct current technology referred to as digital electricity, and then we're going to leave you some takeaways. With that, I'm going to hand it over to Qlai to give you sort of an overall introduction to a microgrid concept.
Thank you, Craig. So the question is, what is a microgrid? The electrical industry has many definitions for a microgrid. One of the definitions from Department of Energy define a microgrid as a group of interconnected loads and distributed energy resources within clearly identified boundaries that act as a single controllable entity with respect to the grid. A microgrid can connect and disconnect from the grid to enable it to operate in both grid-connected or islanding mode. Let's present various components of the grid. Generation. Generation components can be renewable type as solar photovoltaic, wind turbines, small hydroelectric plants, or biomass plants, or non-renewable emergency generators, microturbines, etc. The storage for energy is optional, but can be storage batteries, flow batteries as known regenerative batteries, kinetic energy or flywheels, or simply compressed air energy storage. The third component are the loads. The loads can be as defined AC type loads, motors, HVAC appliances, etc., or DC loads, high efficiency motors, appliances, computers, servers, etc. Controls is the fourth component and is a device that provides communication between distributed energy sources, grid, photovoltaic, wind, storage, and loads to maintain acceptable level of frequency and voltages. And the last one, it's the grid. The grid gets connected to intelligent breakers that can disconnect or connect the grid back to the source. An AC microgrid have only AC components, and the components are utility generators, wind turbines, and AC loads. A DC grid or microgrid have only DC components plus the utility, solar, batteries, DC loads. And a microgrid also can be a combination of the two. It's exactly what you see in this slide, call it as a hybrid AC-DC microgrid. The microgrid sizes can be defined by voltage level, phase, kW of peak load, kW of generation capacity, kW hours, or number of customers. The usual size of a microgrid is between hundreds of kW to few megawatts. If a microgrid is sized between 50 to 100 kW, we can call it as a nanogrid. If a microgrid is sized less than 50 kW, it can be called a picogrid. Nanogrids and picogrids have the same components as the microgrid, but at a smaller scale. The nanogrids and picogrids are usually deployed for small commercial buildings and residential solar photovoltaic systems. The microgrid provides power to campuses, small urban and rural areas, or small commercial buildings, or even for a simple house. The microgrid could be the answer, or our answer, industry to the energy crisis by encouraging use of the renewable sources. Transmission losses get highly reduced by using the microgrids by not overloading the existing transmission lines. Installation of microgrids results in substantial savings and cuts emissions without major change in lifestyle. Greg, can you move to the next slide, please? And here you go, AC to DC. When it started, starting in the late 1880s, Thomas Edison and Nikola Tesla were involved in a battle now known as the War of Currents. Edison developed direct current that ran continuously in a single direction, like a battery or a fuel cell. During the early years of electricity, direct current, shorthanded as a DC, was the standard in US. But there was a problem. Direct current is not easily converted to higher or lower voltages. So it couldn't have been transmitted to longer distances without a lot of spending in adding multiple substations. Tesla believed that alternating current, or AC, was the solution to this problem. Alternating current reverse direction a certain number of times per second and can be converted to different voltages relatively easy using a transformer. The Chicago World Fair, also known as the World Columbian Exposition, took place in 1893 at the height of this war. General Electric bid to electrify the fair using Edison direct current for almost $500,000 then, but lost to George Westinghouse, who said that he could power the fair for only less than $400,000 using the alternative current of Mr. Tesla. The same year, the Niagara Falls Power Company decided to award Westinghouse the contract to generate power for Niagara Falls. Although some doubted that the falls could power all the Buffalo, New York, Tesla was convinced it could power not only Buffalo, but the entire eastern United States. On November 16, 1896, Buffalo was lit up by the alternating current from Niagara Falls. By this time, General Electric had decided to jump on the alternating current too. It would appear that alternating current had all but obliterated direct current, but in recent years, direct current has seen a bit of a renaissance. Today, our electricity is still predominantly powered by alternating current, but computers, LEDs, solar cells, electrical vehicles, all run on DC power. And methods are now available for converting direct current to higher and lower voltages. Since direct current is more stable, companies are finding ways of using high voltage direct current to transport electricity for long distances without less electricity loss. So it appears that the war of currents may not be over yet, but instead of continuing in a heated AC versus DC battle, it looks like the two currents will end up working in parallel to each other in a sort of hybrid armistice. And none of those would be possible without the genius of both Tesla and Edison. Next slide, please. So what is alternating current and what is a direct current? The alternating current, AC, is an electrical current which periodically reverses directions. And it's used, to deliver power for businesses and residences, and it in a form of electrical energy that consumers typically use when they plug kitchen appliances, television fans, electric lamps. The AC can be delivered in single phase or a three-phase system. The alternating current frequency is the number of cycles per second in an AC sine wave. So the voltage and current, as shown in the graph, change the direction up and down 60 times per second in US and 50 times per second in the other part of the world. The DC current, on the other hand, is an unidirectional flow of an electrical charge. An electrochemical cell is a prime example of DC power. Direct current may flow through a conductor such as a wire, but can also flow through semiconductors, insulators, or even through a vacuum as an electron or ion beams. Direct current may be converted from an alternate current supply by use of a device called rectifier. On the same time, the direct current may be converted into the alternating current via a device called inverter. So next slide, please. So let's talk a little bit about the common voltages and application for alternate current and direct current. The AC side of the distribution has matured over the last 130 years and standardized the utilization voltage to the following: 480 volts for commercial, 240 volts residential appliances, 208 volts commercial distribution, 120 volts residential or commercial. On the other hand, the DC market had not developed standard voltages level yet. So in today's market, we are going to see a lot of voltage levels, such 380 volts from emerging alliance distribution voltage, 60 volts on commercial for power over internet system, 48 volts, 24 volts, 20 volts, 12 volts, 5 volts. The Emerge Alliance is the Open Industry Association developing standards of DC power distribution in hybrid houses and commercial buildings. They are going to standardize to 2 voltage levels to be used, 380 volts and 24 volts. The circuits using voltages greater than 50 volts are called line voltages, sometimes class 1 circuits that are not safe to operate live, where the circuits using voltages less than 50 volts are called class 2 circuits. These class 2 circuits, were limited to under 100 watts, are safe to touch. And this presents a big opportunity of savings by not using high-skilled labor or needed, or they're able to use actually the light. 50 volts is not going to kill you. So, Craig?
Great, thank you, Q-Line. So thank you for the introduction, explanation of AC and DC. I'm going to talk now quickly about why DC provides potentially an attractive alternative. So we're using DC power throughout our buildings, and we're really having to live with the legacy of AC power due to the fact that it's the source. So on the left here, we see all of the accessories that we typically require to power a home or a business from alternating current. And then on the right, we see the loads, whether they're computers, phones, lights, the components of a microgrid, batteries, and solar that are now becoming more commonplace in our buildings. And because of the legacy of the war of currents, we have a lot of AC sort of infrastructure that is required to rectify the AC power to a useful DC power. All of these components that we refer to as bridges in some cases indicate or are typically the lowest point of reliability in a system, are a form of great inefficiency of energy loss and an additional complexity and cost. So by adopting or looking towards an all DC power typology, we can look to remove all of these accessory devices that are only there because of the legacy of AC being the prevalent power distribution typology. So let's take a look at a typical 1-bedroom apartment. and look at the devices that require power. So here's an electrical layout, and I've added some annotation here to suggest what the power demands are of all of those devices. So receptacles, lights, appliances, HVAC equipment, and ultimately the voltage ratings that each of those devices requires to operate. So in this slide, I've annotated what the actual demands are for those devices. If we ignore the fact that in an AC world we only have 120 volt AC to deliver, and in fact, all of our LED lights, the majority of the receptacles that we use for powering convenience appliances, telephones, desk lamps, clocks, etc., all require a lower voltage, something below 60 volts DC. So the opportunity to replace all of those devices here shown in blue and purple with a low voltage device is real. When we look one step further and at the appliances that typically dictate the largest amount of power demand in a residential unit, and that we typically supply with 240 volts AC, higher voltage class power, the majority of the appliances that you purchase today or you specify on a project actually are DC driven inside. And that's something that's happened over the last 20 years as appliances go towards more of a smart appliance configuration that have additional digital controls that use inverter technology and that have basically put all of the power distribution within the appliance on the DC side. So again, the potential exists to replace those 240 volt AC appliances with what is somewhat becoming the standard of a 380 volt DC typology. So if we look at the remaining needs in a residential unit that are alternating current inherent demands, they're very limited. So this helps to build the case for why does DC a useful technology to look at in this day and age. So efficiency is something that's often overlooked in the electrical distribution world because ultimately our opportunities for putting in more efficient or more unique infrastructure is typically limited. But when looking at AC power distribution versus DC power distribution, in this analysis, we've added the components that the building would see between the source, being the utility coming into the building, all the way to the actual LED fixture, so the LED in the bulb that's creating useful light. And this is an analysis that shows that if we were able to remove some of the AC to DC conversions, we would actually achieve a percentage savings, between 81% to 86%. So, over almost a 10% improvement in retained energy consumption to drive that LED. When we look at a microgrid typology, where we have solar and batteries that are being used to power those loads within a building, the inefficiencies associated with generating DC and then converting to AC to store in DC in your batteries, and then to draw out again and convert from DC to AC before distributing in the building, and then finally converting from AC back to DC at that LED light fixture, the amount of opportunities for energy loss is compounded. And this calculation shows that the amount of electricity we're able to retain from that kilowatt hour of electricity generated at the solar panel jumps from 62% to 75% when following a DC building typology. So that's why DC power and DC microgrids, especially as they pertain to highly efficient net zero energy buildings or buildings that include some component of solar and storage, is particularly relevant in this day and age. The USGBC, through their LEED accreditation program, has recognized this. There's many individuals in different organizations that have spent a great amount of time canvassing for more attention to DC power and the efficiency associated with it. So LEED has now introduced a pilot credit for DC power systems. And I encourage you all to look at it and consider it for your next projects. And with that, I'll hand it back to Qlai to talk about some of the control opportunities that exist with DC power. Qlai, you may still be muted.
Sorry. Direct current power, or power over Internet. To distribute DC power to many available devices on the market, an IEEE standard technology called Power over Internet, or PoE, is used. The Power over Internet describes any systems that pass electrical power along with data on twisted pair and Ethernet cable. You might be familiar with the Ethernet cable from low voltage and data. This allows a single cable to provide both data connections and electrical power to devices such as wireless access points, IP cameras, motion sensor, daylight sensor, which allows to deliver more effective energy savings policies by implementing daylight harvesting or tighter timeouts. There are several common techniques for transmitting power over Ethernet cables. 3 of them have been standardized by IEEE standard 802.3, as shown in this table. And this standard is known as alternative A for type 1, alternative B type 2, or 4PPoE. The original standard 802.3 was developed in 2003. And this standard provides up to 15.4 watts power to each port, but only 12.95 watts is assured to be available at the power device, as shown on the top of the table. Looking at ways to increase the amount of power transmitted, IEEE has defined another standard, IEEE 802.3BT, 4PPoE, in September 2018. The standard introduces 2 additional power types up to 60 watts that deliver 51 watts to the device, and type 3 up to 90 to 100 watts that is able to deliver up to 71 watts at the device. This development opens the door to new applications and expands the use of applications such as high-performance wireless access points and surveillance camera or office distribution receptacles where you can plug directly your laptop or desktop. Nowadays, the laptop and the desktop use an average of 50 to 60 watts. So using this PoE Ethernet type 4 will deliver enough power for you to use that receptacle. The power over Internet is delivered over category 5 or better cable to a maximum distance of 328 feet. So you have a better opportunity to use, these cables for longer distances without worrying much about the voltage drop. PoE installation reduces materials and labor costs by using a single Cat5 or 6 or better connection for power and communication. This greatly simplifies the installation process, saving time, minimizing safety risk. Next slide, please. The direct current power USB universal serial bus. the industry developed specific DC connectors to power all DC devices. The Universal Series Bus USB is an industry standard that established specifications for cables and connectors and protocols for connection, communication, and power supply between computers, peripherals, and other computers. The standard was released in 1996 with the first generation ESB1. After that, they follow with the more upgrades on USB 2. And in 2011, they developed the USB 3 that allows a super speed transmission data up to 5 giga. The 2014 was followed by the USB 3.1 and 3.2 in 2017. And in 2019, the latest and greatest is the USB 4 that allows super speed up to 40 gigabits per second. As you see in the receptacle socket identification, the standard ones are the Type A, Type B, that everybody is familiar with them on your phone. The Type B under USB 1 and USB 2, I believe you'll see it a lot on the printers. And then, after releasing the USB 3.2 and USB 4, the industry standardized to USB-C, that nowadays pretty much the phones, the laptops are using it. In the the USB power standard, as you can see on the right, the voltage delivery is either 5 volts or 20 volts. But what is important is the last column that you can, we started with a lower power device of 0.5 watts. And nowadays we can deliver power up to 100 watts. Next, please. So let's see it. The plugs and the receptacles. On the top left corner, you are going to see the traditional USB 1, USB 2, and the smaller one is the USB-C. After that, we find the category 5, 5E, 6, 6A, and 7, the traditional data cable. Then we have a barrel connector plug, followed by an Anderson Safety D-Grid 400 volt AC DC. Most probably, the industry is going to standardize around a cable similar to this Anderson Safety Grid with the following features. Make it first, break last connection. Provide the safety of the earthing path before engagement of the power contact. The hot plug rated, the connectors are rated for current interruption for both electronic and electrical loads. Touch safe, that minimize the risk of personnel contact with hazardous voltages, even at this high voltage, 400 volts or 380 volts. And also provide arching protection. Housing contain the arc if connectors are made or unmated while under load, minimizing risk of personnel. The power density that you can transport with this Anderson Safety Grid, they can go up to 400 volt AC or DC and up to 30 amps. Next, please. The AC DC microgrid hybrid ecosystem components. So in this picture, we're going to show you that different type of components that we discussed previously in the first slide. The utility connection. The connection between the utility and the building on the back is done through medium voltage switches that feed transformers, and they lower the higher voltages, 13.2, 5 kVA, or even higher voltages to a more utilization voltage of 480 volts, 277, or 120, 208. Then we have the on-site generation and the storage. The on-site generation could be PV. Then from the on-site generation in the buildings, you are going to find these blocks of that will help distributing or providing the conversion from the AC or DC to a DC utilization voltage of 24 volts or 48 volts. The Power Hub device is AC. They will be able to receive AC or DC input, and they will be able to deliver low voltage DC output to various components. The same principle also is followed by the Power over Internet switch, but in a smaller scale. The number 6 here is our traditional in ES 120 volts or 125 volts, 20 amps or 15 amp socket that have been added with or fitted with USB Type A or Type B, and also with a USB-C that will help us to, charge our phone quickly and easily from the traditional socket. The next one is the DC-DC driver for the LED fixture. So in order for us to power the LED light, we need this device that will allow connection of this Cat5, Cat6 cables to the LED light. And after that, there are 2 examples of the cables, traditional cables, Cat5e or Cat6e, that they will be able to provide the power and data that is needed. Next. So now we're going to talk about 2 examples. One is the American Geophysical Union, followed by another example that Craig is going to present. The American Geophysical Union is a non-profit professional scientific organization whose members came from different fields of Earth and space science, has a guiding philosophy grounded in a single notion: science for the benefit of humanity. So when the system inside its aging Washington, D.C. headquarters began to crumble, AGU officials has had a decision to make. They could fix the failing systems in the nearly 25-year-old building and leave the rest of the structure intact, or take the whole thing down to its studs and start over. Seeing the opportunity to design an entirely new green workspace, they adopted for the latter. The building will feature a rooftop solar photovoltaic panel installed horizontal on elevated structural superstructure. The design team was implementing almost 22 high-performance strategies. And those strategies, I will name a couple of them: solar photovoltaic, sewer heat exchange system, DC power workspace, direct current LED lighting, dynamic toilet room exhausting, variable frequency drive, occupancy sensor and control, energy usage dashboard display. Some of them, they are impacted directly by the use of DC power. And those are solar photovoltaic PV, dynamic glass shading, daylight responsive control, triple pane glazing. They are using DC power to change their colors, occupancy sensor controls, and energy usage dashboard display. So the photovoltaic, as I said, PV system generates electricity that provides building LED lights, ceiling grid, computer monitors, and workstation. The photovoltaic system is installed on the roof horizontally, but also it's installed vertically on the south side of the roof because the design team needed to increase the amount of surface that is needed to meet a certain power requirements to make sure that the net zero energy requirement is met. So implementing the 22 high performance strategy will provide the AGU with an annual energy building consumption that not more than 300 megawatt hour annually. The PV system itself, will be able to provide almost 346 megawatt hour of energy. Next, please. So here we are showing the DC distribution for the AGU that utilize the existing electrical 208 120 volt infrastructure that was part of the 1992 renovation and the new 380 volt DC microgrid powered by photovoltaic systems. As I mentioned before, the overall capacity of the PV system is approximately 258 kVA based on 717 360 watt sun power module. The design intent for the 380 volt DC microgrid is to directly utilize the generated DC power by the majority of the LED lights and workstation, while any excess power is backfed back to the utility. So the DC microgrid is set up to the traditional AC distribution. Each PV module will generate power at approximately 60.6 volts DC. Multiple PV panels will be connected in series, and that in a string, and that string will convert the voltage to 300 volts DC using a string optimizer. The string optimizer will be connected in parallel and will be combining combiner boxes and fed into the 300 volt DC bus that is shown on the top of this diagram. The same 380 volt DC bus will also be fed from a second source that's supported during nighttime and cloudy days, because we know sun is not available 24/7. That second source DC is an AC-DC rectifier fed from the local utility, and that is the LTEC 90K WACD rectifier that will take power directly from the AC and will be able to power the 380 volt DC. For the DC microgrid to function as described above, it will depend on the 380 volt DC voltage levels produced by the PV system and a voltage set point assigned to the inverter. The voltage set point assigned to the inverter will allow the inverter to only invert the excess power produced by the PV system. This set point is typically between 382 volts DC and 383 volts DC. So during the day, we are going to experience three different scenarios for the PV production. When the PV power generated is larger than the DC load power consumed, the DC bus voltage will rise slightly above 380 volts. And once it reaches the set point, the AC will be backfed to the utility. When the power generated by PV is equal to the DC load, then the voltage will remain constant at the DC bus, and the PV will continue feeding the DC load. If the consumed power by the DC load is more than generated PV power, the rectifier will convert the utility power from the AC to DC, supplementing the remaining power required by the bus. Craig, next one. The original DC distribution concept was to provide the power supply that is going to provide power to an energized DC grid, ceiling grid. Unfortunately, one of the suppliers was not able to provide the actual connector that is shown on the right-hand side. So the design team then decided to go directly and feed every single light with the cables from the power supply to the lights, AV securities, and other components. Next slide. So this is the power driver or power hub driver that was supplied to AGU, and it's receiving power directly from AC system or DC system, but not in the same time, and delivers low voltage 24 volts to the various loads. So the power supply has available 16 channels, each channel able to deliver 100 watts. Only 15 channels will be used to power LED lights or receptacles. The 15th one will be designated just for the controls. The receptacles that have been used at the AGU are the ones that are showing on the right-hand side. And you see there are Type C ones or a combination between Type C and ESB 1 and 2. Next.
Cool. Thank you very much, Eli, for that project review. I'm going to sort of rattle through the last slides here relatively quickly so we keep some time for Q&A. So please stay with us as we sort of finalize the presentation here. So this is a project that we have. It's in construction. It's in Virginia, Arlington, so closer to the DC office. It's a single family home going to be built to FIAS plus net zero rating. Very engaged homeowner who understands where the trends are going with DC power and DC devices, and wanted to look at an overall DC power typology for the entire house. So we've been working with them for the last few years on really the analysis and specification of DC loads in the home and integration with the solar and storage technologies. So I'm going to keep this relatively high level and show you how a traditional home is powered. So a traditional home has an AC utility connection, a meter, an AC panel that then serves the AC loads in a house. When you add solar and onto a conventional house, you're placing a DC source, the solar panel on the roof. You have to pass it through an AC to DC inverter to make AC power to then feed into your panel and AC loads. When you add storage, so a battery storage functionality into that same system, you have to add your batteries. You have to add a separate inverter. So now you have two inverters in order to take the power that's generated from the solar, convert it to AC, direct it to an inverter to generate DC, store it as DC, and then again to pull it back out. And you can probably appreciate the inefficiencies that are associated with that. In comes what we refer to as a DC coupled and a DC coupled hybrid inverter. And what this device does is it incorporates a DC feed from the solar, but rather than inverting it to AC to be used or stored, there's a DC side to that equipment. And we can then supply power generated from the solar to batteries and to DC loads off of that one inverter system. So that's how we've basically organized the house electrical infrastructure for this home in Virginia, and we've identified a number of the electrical loads in the house that can be fed off the DC side of the hybrid inverter. Because of the nature of the house being fairly custom and high end, there's quite a functional electrical system to go with it. But we are looking at another project currently that's looking at more of an affordable, lower cost typology for a DC coupled microgrid that can streamline some of the equipment and functionality. So the one piece that we wanted to leave you with that we think is potentially going to be disruptive to the entire DC power system is the concept of digital electricity. So digital electricity is basically the same as direct current, as Kulai introduced earlier, but it overlays communication on the same pair of cables. And it does that at a frequency, 700 times or so a second, that it can tell by monitoring the power line whether there's a fault on that line. And the ability to monitor and assess where there's a fault allows the technology to cut power, so to stop the flow of current through that conductor to maintain safety on that line. What that means is you can supply high voltage or 380-ish voltage DC power over a set of cables that would be treated the same way as what we refer to as class 2 power. And that's what QLI had referred to earlier as power limited, so under 100 watts and nominally below 60 volts DC, which can be installed by a non-licensed electrician in many jurisdictions, does not require many of the hard protective natures that electrical systems typically come with, including metal conduit and junction boxes, and can therefore achieve lower cost installation while providing higher amounts of power. So a project that we've been working with and a client that we've been working with on a number of applications is Sidewalk Labs. They've actually built out a form of this digital electricity system in one of their locations. And what you see here is basically where the digital electricity originates, and it's on sort of computer shelf type equipment. The distribution wiring, so not in hard conduit, but this is 380 volt DC power, which would typically be unsafe. These are receivers, so this is where the digital electricity is converted back to more conventional DC power. So this is a low voltage receiver, and it puts out, as you can see on the far right, power that serves more a conventional desktop type uses like USB receptacles. The receiver on the top outputs a higher voltage, so closer to 380 volts DC, that can power large packaged white goods, so appliances. These are actually appliances that have been manufactured using 100% DC power, so they will not accept an AC input. So this is meant to illustrate that the potential for DC power is very much there, and there are certain applications, clients that are interested in sort of spending the time to learn about it and the potential benefits. One of the main benefits that we've seen through our work with Sidewalk Labs is the potential for flexibility in general construction. Traditional wall requires hard fixed infrastructure behind the wall. If you want to adapt it or move it, there's a fair amount of demolition and hard infrastructure that needs to be moved. With digital electricity that's potentially run through baseboards rather than hard conduit, it can be easily moved or taken out. Doesn't require licensed electricians to do so. It provides more flexibility in the use of our spaces. So takeaways that we think are important for attendees: DC power through the more clear split of lower voltage class 2 power has the potential to reduce installation costs. It has the potential to be the backbone to digitizing electrical infrastructure in a way where you're not putting in parallel systems to provide the same outcome. There's energy efficiency gains that are potential that are really just now starting to be understood, and there's a lot of research that's happening at the national lab level to better understand that. Provides more flexibility in the future, which we think is very pertinent to our current going back to work post-COVID or during COVID reality, where investments space use planning is potentially uncertain as to what and how long it'll be permanent. Digital electricity direct current power allows very flexible tenant improvement and layout options. There's LEED credits available. This just the basic, there's so many loads in a building that are DC. Why are we providing them with AC? The fact that it's a key enabling technology to enable electrification, decarbonization of our grid. A quick plug for our next webinar, which will be in 2 weeks from now on radiant systems. So look for that from our LinkedIn page or our mailing list. It'll be a great lecture. And now we'd be happy to take question and answers from anyone who's got a burning direct current question. And Kulai, maybe you've had a chance to look through some of them.
Yes, I did. I saw only one question. If we can get a copy of your slides, and definitely you will get a copy of the slides. A copy of this seminar will be made available.
Great. Are there any other questions? We do have 5 minutes left. Otherwise, we'll park it there. And thank you all for attending. Okay, thank you, everyone.
All right, thank you, Craig. Thank you, Kulai. That was a great presentation. If anybody does want to drop questions in, we will be circulating a Q&A document along with the information on the AIA certificates. So thank you so much for that, and I hope everybody has a wonderful day. Take care.